Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X, published on February 16th, 2026, about 5 days ago. It demonstrates that the geometric structures emerging in large language models, like calendar months organizing into circles, are mathematically inevitable consequences of translation symmetry in language statistics. The paper is titled, Symmetry in Language Statistics Shapes the Geometry of Model Representations. And as we'll see later, the way these structures remain robust even when data is removed is really quite remarkable. Figure 1 provides the visual evidence for this claim, directly comparing theoretical predictions against real model data. The top row illustrates the theory. Purely based on translation symmetry, calendar months are predicted to form a perfect circle, while historical years create a smooth curve. Moving down to the middle and bottom rows, we see actual results from standard word embeddings and the Gemma 22B model. Remarkably, these empirical plots almost perfectly mirror the theoretical ideal, confirming that simple statistical rules essentially force the models to adopt these specific geometric shapes. Well, while Figure 1 established the general shape, Figure 2 digs into the fine-grained structure. On the left, the authors project the high-dimensional embeddings for years onto 2D planes, defined by different principal components. The theory predicts these should form looping patterns called Lesagis curves, which are shown in the top row. The bottom row plots the actual word embeddings for years 1700 to 2020, and they match the theory almost perfectly. Then, the chart on the right quantifies this by decoding the specific year from the embeddings. The error drops steadily as the model uses more dimensions, tracking the theoretical prediction shown by the black line. So moving from time to space, Figure 3 applies the same theoretical framework to geography, specifically the 48 contiguous U.S. states. The leftmost column visualizes the theoretical prediction, where colors represent principal components derived purely from the physical distance between states. Notice how they form smooth, wave-like gradients that shift clearly across the map. The remaining columns display the actual patterns learned by word embeddings and the Gemma 22B model. The striking similarity confirms that these models effectively reconstruct the two-dimensional map of the U.S. solely from the statistics of how state names appear in text. Well, Figure 3 confirmed the spatial patterns, and now Figure 4 tests their resilience. The authors conducted an experiment where they removed all direct connections between months, shown by the large zero block in the leftmost matrix. Surprisingly, the embedding plot next to it reveals that the months still organize into a perfect circle. The right panels demonstrate why this happens. They show that the model leverages indirect correlations with seasonal words, like winter, ski, or flower, which act as anchors to reconstruct the full time cycle. Alright, Figure 9 now offers a deeper look at the mechanics behind those historical year representations. It breaks down the embeddings into their first 8 eigenmodes for the years 1700 to 2000. The smooth red curves represent the theoretical prediction, while the jagged blue lines track the actual data. Notice how the lower modes in the top row form broad, slow waves. In contrast, the higher modes in the bottom row oscillate much more rapidly, confirming that the model effectively learns a Fourier basis to encode time. Wrapping up, the big takeaway is that the geometry inside AI models isn't random. It is mathematically forced by the symmetry of language statistics. This implies that models learn concepts like time and space simply by absorbing the collective statistical structure of text. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.